Hello, so today we talk about the direction fields, and what we want to know is what are direction fields and why do we need them? So it's possible that now that you know what the differential equation is and you want to find solutions, it's possible that you cannot find the exact solution of the differential equation. And the question is, how do you then understand the behavior of the solutions of such differential equations? Then the one of the answers that can come to your mind is, why not use direction fields? So for you to use direction fields, you need to know what they are, and then what they tell us about the differential equation and its solution. Okay. So basically, in that respect of item number 2, you then need to sketch the curves without solutions. So you get solution curves without knowing the exact solution of the equation. And of course, once you have those solution curves, they can give you an idea of how the solution behave close to a certain particular point, or at infinity or minus infinity. Now, when we talk about behavior at infinity and minus infinity, we are talking about the long-term behavior. So in other words, we're going to say, what is the limit of the solution as x approaches infinity or as x approaches minus infinity? That's long-term behavior. Okay, so we will start off by just defining a direction field. So you have this set of line elements. So these are lines that are drawn at every point xy. So you are in the xy plane, and you want to draw these line elements that defines the slope, or fxy, if we consider the differential equation of this case. So remember, the left-hand side is a derivative. So f is actually representing a derivative. So when you substitute f xy at a point x naught y naught, you're going to get the slope of the curve at that point x naught y naught, where x naught y naught are specific values. So for example, you can have 0 0 or the 0.11 or whatever the case might be. So f of x in this case is actually defining the slope of the function y. F of x, y defines the slope of a function of the function y, whose solution we don't know. Remember, because we have a derivative, to find the solution, we need to integrate, and we have to find y as a subject of the formula as our unknown variable. But we can't, because it's not easy to find to solve all differential equations. Some of them are difficult to solve using the standard methods that are available. So what we do now is to just look at the behavior of the solution based on the derivative. So we're not going to do any integration here. We are not attempting any integration, but we're just going to be dealing with the derivative itself. It will tell us more about what we want to know about the solution. So now what will happen is, for example, we have this point here, 1, 1, the point 1, 1 here. So we want to find what is f of 1, 1. Okay, what is f of 1, 1? So for example, let's say f of 1, 1 is equals to 1. 1, this is basically the derivative evaluated at the point 1, 1. So this is the slope, 1, 1. So there are two things to talk about this slope. 1, the slope 1 itself, 1 is a positive number. 1 is greater than 0. So we are saying we have a positive slope. And 2, 1 can tell us about the orientation of the line element at the point 1, 1. So whenever we substitute the value of the derivative at a given point, if we evaluate the derivative at a given point, we have two things to talk about. One, the slope, the sign of the slope, whether it's a positive slope or a negative slope. Or two, the orientation of the line element. So what it means is we will go to a point, let's say this is point 1, 1. So we assume that we have some axis, the x and y axis at that point. So we know if the slope is equal to 1, then it means we have moved one step in the x direction and one step in the y direction. Okay, so which means we will have to have a slope of this nature. So we can easily then say this is the line element at the point 1, 1. Because of that, 1, the slope is positive, and 2, the slope value is equal to 1. We can determine the orientation of the line element passing through the point 1, 1. In fact, this is some tangent line passing through the point 1, 1. So we just want a small line. So whatever you are now seeing here in this graph here, this is just an illustration. It's just saying at this point we have a positive gradient. Here it's horizontal, so that is the gradient is 0. Here you can see it's a negative gradient, positive gradient. So this is positive, 0, negative gradient, negative gradient, positive gradient, positive gradient, positive gradient, positive gradient, positive gradient. So the orientation will tell you how steep that line looks at that point. Depends on the value of the what? Of the derivative. So for example, if we have the value is equal to, let's say 4. So this is the slope. So basically you are saying the orientation should be in such a way that if I move one step in the x direction, I should move 4 steps. So the line should have an orientation that if projected, it will pass through that point 4, 1, like that. So at this point, I can just put this line element here slightly close to the vertical line or to the vertical axis because of the quantity, the value of the slope. Okay, so what it means is if the slope was equal to 0.5, then you would see that the orientation will be leaning towards the horizontal axis. So that's all we need. If we know how to play around with the slope, the value of the slope as telling us whether it's positive or negative, and of course the orientation depending with the size of the slope, you can actually see that the line element could be leaning towards the vertical axis or or towards the horizontal axis. All right. So that's all we need to know about the line elements. Now, if you are given a set of points, like in this case, where at every point you put a line element, this graph now with these line elements at the given points is now called the direction field of the solution. All right. So how do we draw the direction field? So there are 3 ways that we're going to use here. One, we are going to use the given rectangular grid, or you can also use what are called nowclines. Nowclines are points, the set of points at which the derivative is 0. Or you can use isoclines, which are the set of points at which the derivative is always constant. So we're going to deal with those three, and those are the points of emphasis for this for this chapter and for this section. Now we are given the differential equation, and then you are asked to draw the direction fields for the differential equation at 9 points. At 9 points, xy generated by the values of y given in that as minus 1, 0, and 0, 1. So basically, what you will then do, now in this case is to generate the points first. So you generate the point first. Once you generate the points first, then you let me stop this one here and share. Let me go to the whiteboard. So basically now you are given that dy dx is equal to 1 over y squared. So in this case, your f of xy will be equal to 1 over y squared. All right, so then now you are given that x should take the values minus 1, 0, 1, and y should also take the values minus 1, 0, 1. So you want a grid where a grid of points where let me erase this. So you want a grid of points x, y on the x plane, xy plane where you have minus 1, 0, 1, minus 1, 0, 1. So the mixture of points there, you will then find that you have points like this point here, 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 this point here. So let's count them. Yes, 3, 3, 3, that's 9. So now we want to determine the value of the derivative at that particular point. So let's do a table here and see what will happen. So the point is the xy point, then dy dx is equals 1 over y squared. And then now we go now to check what is the orientation that we can get there. All right, so there we are. So we have points. So I'm starting from here. So I have the point minus 1, 1. I have the point going down. I have another point minus 1, 0. I have the point minus 1, minus 1. So I'm done with those. And then the next line, I have 0, 1, 0, 0, 0, minus 1. Then the next one is 1, 1, 1. Okay. 1, 0, and then 1 minus 1. So at each of the points, we need to evaluate the derivative. So by writing minus 1, 1, then it says this is the x value and this is the y value. And since this is a function of y only, we can only focus on these values here, only the y values throughout, and forget about other things. the x values won't work because we are basically evaluating only y there and there is no x. So now if I evaluate there 1, I have 1 over 1 squared. So this is 1 over 1 squared, which is just 1. So this is a positive slope. And then I have 1 over 0 squared, which is undefined. Okay, I cannot say anything. Then 1 over minus 1 squared, then this is equal to 1. This is the same as the first one, so I get a 1 there. This is the same as the second one. I get the undefined. So I can easily do this so that you see which one corresponds to what. So let me do that for all of them. So then minus 1 is similar to that one. So I have 1, wherever there's 1, and wherever there's 0, it's undefined. Wherever there is minus 1, I get the slope 1. So all my slopes at all other points are just greater than 0, except at 3 points where this is undefined. So what do we do? So we now need to put the line elements. So let's go and put the line elements. Let me remove the break there. So we want to put the line elements. Now let me put green. Let's put the line element. So at the point minus 1, 1 here, there is there's a positive gradient or the positive slope. So the orientation should just be from the top left to bottom right, from the bottom right to top left. And then here, when it's undefined, the orientation is vertical, because wherever we have an undefined derivative, we have a vertical asymptote. And then here, the orientation is like that. Orientation is like that. Vertical orientation is like that, vertical, like that. So there are 3 points: minus 1, 0, 0, 0, and 1, 0. So wherever y is 0, we're going to have a positive vertical orientation. So we have this vertical orientation here, vertical orientation here, vertical orientation there. Okay, so this is the case. So now at all others, we have the derivative is equal to 1. So the slope is just like forming a 45-degree angle from the horizontal and the vertical axis at every point. So we're going to have something like this. And there we are. We now have our direction field. We now have our direction field. So what you will then see is as we move from, let's look at this direction here. From x is equals to minus 1 to x is equal to 0. We start with this orientation. So somewhere here we will see that orientation, but it will change. Why? Because by the time we reach the value x is equals to 0, we need to have a vertical orientation. So, and then from x is equal to 0 to x is equal to 1, so we're having some positive orientation, but we make sure that by the time we reach x is equal to 1, we would have an orientation that is landed with slope 1. So then we can then say, if we use that argument, what we will see now is the curve is most likely to do this and that. So that is the solution curve. And we can also do the same with the other ones and see that The cave is most likely to do that. Then we can see that the cave is most likely to do that, and so forth and so forth. So these will be the family of solution caves that we can make out of this. All right. So that's how you get. So, but first of all, before you put these solution caves, you only need the direction field. What we had with arrows there, with those linear elements at every point, is what we call the direction field. But when we add solutions, then we now have solution caves on the plane. All right. So that's what how you do it when you are using the defined points on a grid.